Hello, and welcome to the Ties that Unbind. My name is Marwan Fayed, and I'm here to talk about work to decouple IP from the service names and sockets with which they're commonly associated at CDN scale in order to achieve something we're calling addressing agility. This work, of course, is in collaboration with many people at Cloudflare, as well as a few familiar names at Virginia Tech, Maryland, and Northeastern. Let's first begin by trying to define addressing agility. We think of addressing agility as being the ability to reuse, or reassign, or reallocate IP addresses in a manner that is isolated and independent from the names and the processes to which they're commonly bound. And I'd like to actually begin by sharing some of the lessons that we learned in the end. Namely, one of them, how many names can we associate with a single IP address? I can confidently say no fewer than 20 plus million. Second thing we've learned is that when we want to change addresses, the rate at which we can change them is as fast as per DNS query. And lastly, when we want to change them, we can do so for any reason. This is to reflect policies instead of name changes. And in the end, this opens up an interesting question, which is what new systems and features do these observations enable? And I'll just touch upon those at the end. But why do we need addressing agility at all? It turns out that at scale, address bindings actually become a bottleneck, and they get in the way of being able to respond, adapt, be flexible, and actually impede innovation. This is, in part, a consequence of 40 years of legacy that started with one name, one machine, and one or maybe a few IP addresses. And as a result, we have something that I've chosen to represent intentionally with a narrow waist, which is this idea that host names are often associated with IP addresses, bound, and similarly IP addresses to interfaces and sockets. Now on the surface, this doesn't sound like a terrible thing, except that when you want to make changes at scale, there's this transitive relationship that emerges where even making changes on one layer, at the upper layers, might have an impact at the lower layers. So as a consequence, any system changes or re-architecting new things costs time and money. Well, the default response, of course, is more addresses. If we restrict ourselves to IPv4, we can see the number of IP addresses associated with a set of CDNs is absolutely staggering. And even more so if we assign the current market value. So I'm here to say, make the claim, more addresses is the wrong solution. If we think about it in IPv4, the scarcity of IP4 addresses increases their cost, but it also locks out new entrants into the domain. IPv6 is great, except that there's so many addresses that it's just far too easy to lose count. From a CDN's perspective, addresses are resources. We in the engineering and science community would say more of any resource is just brute force thinking. Resources should be scheduled, and this is the position we're taking about IP addresses as well. So let's look at this, come back to this observation. How do we get out of here? And it turns out, actually, some of the enabling technologies already take us in the right direction, namely name-based virtual hosting in the higher layers with SNI or HTTP host, and IP-based virtual hosting with ECMP and consistent hashing-like mechanisms in lower layers. So let's talk a little bit about the design. Fundamentally, the purpose of this is to return or reduce, I suppose, IP addresses to their original intended purpose if you look at the original RFCs of reachability. And we're going to do so in two ways. At higher layers, we're going to re-architect DNS, and at lower layers, we're going to re-architect sockets to be programmable. And I want to point out here that each of these can be deployed independently, conferring rightful benefits within their respective space. So here's the current view of authoritative DNS on names. A query comes in, we do the lookup on the name and get a bunch of addresses that are matched to that name. Maybe some additional administrative work, and then construct the record and send it back. So this begs the question, if we're going to change the name bindings, where do they actually live? It's not in a lookup table or a database somewhere, as far as the internet is concerned. The bindings actually appear only when a DNS query comes in and a response is sent back. And interestingly, they last only as long as the response sits in a downstream DNS cache, or there's an open connection using that binding. So instead, we're going to re-architect authoritative DNS and ignore the name completely. And instead, when a query arrives, we just apply some policy. for the purpose of this talk, we say, is it arriving in a particular location? Does it sit within a particular account type? And if so, generate a random bit string and append it to a particular prefix. At the lower layers, the socket API is 40 years old. There's lots of great work happening in the community to address its shortcomings. But for this instance, it's enough to say that sockets are too rigid, they're highly unscalable, and they're very much all or nothing. So instead, we've used BPF to architect something called socket lookups, or SK lookups. And the idea is simple. A packet comes in a particular IP port pair. We look up in a dynamically populated mapping table which sockets those packets should be forwarded to. And in a sense, this allows us to carve up the IP port pair space in a way that suits. If you want to try this, it's actually been accepted into the mainline Linux kernel from version 5.9. One of the reviewer's comments asked about transferability. Does this apply to other domains as well? Who exactly can make use of this? It's a very simple definition. If you happen to run a network that has ownership or a service, ownership of authoritative DNS, then you can do the DNS side, which is the name to the IP address binding. And that confers the benefits of policy addressing and some agility. Randomization requires very small source code changes, as we know from experience, but the engine to enable a wider set of policies and how to express them is future work. On the connection termination side, if you have ownership of that, well, you get socket adaptation and flexibility and responsiveness, and conservation, the ability to split up IP port pair space in a way that suits you. Again, this is available publicly now if you want to try it. And we're leaving for future work the systems that remap these IP port pairs for running processes, but measurements are available as well. So just pause here for a moment and say, these are applicable not just to large CDNs, but also to universities and enterprise. Anyone that has ownership over either or both of these. So let's talk a little bit about the deployment and the evaluation. How do we know this is true? Well, first I would like to set expectations and point out the goals and measures of success. If this works, we should have forced no changes on surrounding systems. We should see no observable changes in behavior both inside the system or outside in the wider internet. We should see no performance degradation, and fundamentally nothing should break. So to give you a sense of the size of the Cloudflare network, there are POPs and data centers in 200 plus cities in more than 100 countries. We're going to isolate ourselves to this region up here with 6 POPs taking multiple time zones, the whole of Canada, and we're responding to 100% of all DNS queries for 20 plus million host names that meet the policy objective. The space that we are working within, a single /20 in IPv4 and a /44 in IPv6, everything I talk about in one domain works in the other. The duration of this, if only to give you confidence that this works, from June 2020, IP randomization has been in effect. And then in June 2021, we decided to move to one single IP address for all 20 million plus host names, in order to allay any doubts and fears. This is at one single POP, by the way, just to be a little careful. So when it comes to measuring and evaluating performance, very much the response is there's nothing to see here. And this responds to the reviewer's second main comment about evaluation. Whenever we looked at the before and the after, they were indistinguishable. So let's first share a little bit about the Cloudflare architecture. Every data center at Cloudflare is architected to be the same, as is every server within the data center. And this is to make management simple. Okay? So when a service runs on one machine, it runs on all the machines. Interestingly, no changes to surrounding systems. So the denial of service, the layer 4 load balancing, all of the rest of the application suite, and the distributed cache unaffected. This is a drop-in transparent change. No performance degradation, no observable changes in behavior inside and out, and nothing breaks that we can see. And for the details about why this works, I will point you to the paper. There is one observable difference, however. So there is this notion of when there's a new name, you want to map it to an IP address. A priori provisioning, however, for that IP address or name is rather difficult. And what ends up happening is you get something like this, a very large skew when you look at load per IP address. So on the left, this is the requests per IP, and on the right y-axis, this is the bytes per IP. And what you can see is many orders of magnitude difference before we dropped in our changes. Afterwards, when we randomized on a /20, so this is 4,000 addresses, this was reduced to but an order of magnitude or 2. Later, when we reduced the randomization pool to 256 addresses, barely a fraction of a magnitude for either measure. And so what I can say confidently is randomization breaks nothing, but it can expose weaknesses in system design where those designs rely on IP addresses or associate any meaning to an IP address. Now, if randomization works over a whole bunch of addresses, then why not randomize over a single address, effectively reducing the address pool to 1? Turns out this works really well. In fact, it might be preferable because anything that could be broken by randomization, or at least reveals weaknesses in systems design, is unbroken by the use of one address. In addition, connection coalescing comes out for free. And just again, to give some confidence, this test was originally scheduled for 3 days, and it's now since been 3 months we've left it running. So let's come back to that summary in the observables and talk a little bit about the future. When it comes to names to IP addresses, we see virtually no limit. We can change the addresses as fast as we might choose to, and we can change them for any reason that we might choose. And 2 questions emerge as a result. What new systems does this enable? I refer you to the paper for a description of some of the things that we're thinking about, which include route leak detection and mitigation for Anycast, denial of service protections, and really, really fantastic measurements. One open question, however, is how best to express those addressing policies. This is one I would love to put to the community, and if anyone is interested in discussing it, please by all means get in touch. Thank you.